Without doing any further examples about the Fourier series coefficients, about the evaluation of the Fourier series coefficients, it may be a better idea to jump into the properties, because let me remind you about one thing. The Fourier series coefficient evaluation has a formula. It's an integral, but evaluation of that integral should be your last resort. Okay? If you cannot do anything else, if you are stuck, if none of the properties that we will see may apply, so you may be stuck at some point, then you must evaluate that integral. But other than that, usually you don't take that integral to solve questions. Instead of that, you apply these properties. What do we mean by that? Let's start seeing those properties. They are the Fourier series properties. I'm assuming that a periodic waveform x of t has Fourier series coefficients ak and a fundamental frequency omega 0. Okay, we have this kind of a notation, let's assume. Starting with the linearity property. The Fourier series coefficients obey the linearity property, but you have to be careful about whether the coefficients correspond to the same frequency or not. What I mean is this: if x of t corresponds to ak and y of t corresponds to Fourier series coefficients bk, some other set of coefficients, and they have a common frequency omega 0. This is very important. These two must correspond to the same period or the frequency. So, for example, if the period of one of them is 2 and the period of this one is 3, for example, in order to apply the linearity properties that I'm showing here, you must assume that they both have a period of 6, the common period. And 6, with that period, the frequency will be equal to 2 pi over 6 or 1 over 6. And the k indexes must be evaluated with respect to that frequency. Okay? You have to be careful about that. Otherwise, if they have completely different periods or something, then this linearity property that I'm going to write doesn't hold. You cannot solve your questions this way. What I say is this: if you construct a z of t as a times x of t plus b times y of t, a linear combination of these two periodic sequences, then the summation, by the way, will have a period 6 for the previous example, as you see. Then this thing has Fourier series coefficients, which are, let's call, ck's, is equal to a times ak plus b times bk. AKs are Fourier series coefficients of x, and BKs are Fourier series coefficients of y. But as I say, this holds only if the periods are the same. You have to be careful about that. So don't jump into the conclusion that you have two separate waveforms with different periods or frequencies. So I'm adding up those two things, and these CKs are just additions of the previous Fourier series coefficients. It's not possible if the periods are not the same. Okay, the other property is time shifting. What happens if you shift your original x of t by an amount of t0 to make a y of t? In other words, what are the Fourier series of y of t with respect to the Fourier series coefficients of x of t? X of t is only shifted a little bit. The derivation of, by the way, these properties can be all proven. They are not some magical formulas or anything. They are theorems mostly, and they have proofs. Some of them are obvious, like this one, because an integral, the integration is a linear operator, and since ak is, or the Fourier series coefficient corresponds to an integration, inside the integral if you add two terms, then it's the integral of this term plus the integral of the other term. That's a linear operator. So this is quite obvious. This one is quite easy as well. The Fourier series coefficients of y of t I'll call bk, and that is equal to, by shifting, the period doesn't change, and the integration duration is t, but the starting point is arbitrary, x of t minus t0, which is y of t, e to the minus jk omega 0 t dt. This was the formula. And this t minus t0 thing, let's substitute to make it tau, 1 over t. This integral doesn't change because it doesn't matter where you start for this duration of t. X of tau, and here we have e to the minus jk omega 0. Instead of t, we can write it as tau plus t0. Okay, with respect to tau, since t minus t0 is tau, then t is tau plus t0. And we can write d tau here, because d tau is the same as dt. Tau is t minus t0, d tau is equal to dt. Their differentials are the same. What is this? This term, exponential term, is e to the minus jk omega 0 tau times e to the minus jk omega 0 t0, isn't it? And this e to the minus jk omega 0 t0 has nothing to do with tau. It can be taken out of the integral. It's a scale. So we have e to the minus jk omega 0 t0 times 1 over t, integral over t, x tau e to the minus jk omega 0 tau d tau. And this portion is ak, the Fourier series coefficient definition of x. So what did we have now? bk is equal to this exponential term times ak. So I'm going to write it like this. bk is equal to e to the minus jk omega 0 t0 times ak. This is a very useful property. It is telling us that if you know the Fourier series coefficient of a signal, then the shifted versions Fourier series coefficients are just the same Fourier series coefficients multiplied by these exponential terms. And this complex exponential term depends on t0, the amount of shift, as well as which index it corresponds to, k, in other words. Do we have an example about this? Well, although we don't have that example yet, but we're going to use this property with another property that we will see. We will combine them anyway. So let's not give an example of this one, but the example that I was thinking of was this. Do you remember that the first and the only example that we saw was the Fourier series coefficients of this thing, right? This signal. Now, what are the Fourier series coefficients of this signal then? It is just shifted by an amount, a certain t0. And whatever that t0 thing is, whatever it corresponds to, you just need to sample by sample multiply these AKs with this complex exponential. Now, do you remember the rule that I was saying? The Fourier series coefficients magnitudes must decay as k increases. But now, these AKs may be decaying for this one, top example. For this one, those decaying things are multiplied by this thing. So are the magnitudes of BK decaying as well? Can we say that? It depends on, of course, the magnitude of this term. Exponential, complex exponential. What is the norm, the magnitude of an e to the j theta? What's the magnitude of it? One? Yeah, it is 1. And e to the j theta has a unit norm. Therefore, the magnitude of this thing is 1. It doesn't really affect the magnitude of BK. The magnitude of BK depends on the magnitude of AK. The norm and the magnitude of this exponential term is 1. It doesn't change anything. It is just incorporating a phase factor, and that phase is this shift anyway. Okay, nothing else. So the same rule applies. If AK is decreasing, BK is also decreasing. The norms don't change. Only a phase term comes into the picture. This property, it's quite specific. That is time reversal. If y of t is equal to x of minus t, then what can we say about the Fourier series coefficients of y of t, which are bk's? What can we say about these bk's? Now, if we want to write x of minus t in terms of the Fourier series coefficients, m from minus infinity to infinity, which is y of t, of course, bm times e to the j m omega 0, making it negatively indexed doesn't change anything. But notice that the question that we have solved was regarding this one. And here, if this is x of t, that is also equal to x of minus t because it's an even signal. It is completely symmetric around the origin. Since x of t is equal to x of minus t, I can say that a of k is equal to a of minus k. But for this signal, for example, it would be different, because this is not a symmetric sequence. So in general, symmetric or non-symmetric, whatever it is, if y of t is equal to x of minus t, then the corresponding Fourier series coefficients are the opposite indexed or negative indexed Fourier series coefficients of the original signal. bk is equal to a minus k, in other words. The fourth property is the time scaling. By time scaling, what I mean is depending on the value of the scale, it may be a squeezing of the signal or an expanding of the same signal. So y of t is equal to x of alpha times t. That's what I mean. What are the Fourier series coefficients of y of t? Do you have any intuition about this? If you want to write x of alpha t in terms of the harmonics, e to the j k omega 0 alpha t would be our new expression, because x of t is equal to summation ak e to the jk omega 0 t. You remember that? That was the representation of x of t in terms of the harmonics. Now I'm multiplying all the places where I encounter a t by alpha. So that would make x of alpha t is equal to this thing. Instead of t, I put alpha times t. So what are the Fourier series coefficients? They are AKs, same. It doesn't change. So they have the same Fourier series coefficients. Does it mean that if the Fourier series coefficients are the same, then the signal is the same? But the signal is not the same, it's different. So what's going on? Any suggestions about what's going on here? The Fourier series coefficients are the same. And their combination should give me the same signal, but it's not the same signal, it's a different signal. What is it that changes? The thing that changes is this. Omega 0 changes. Here, the only difference between this expression and the previous expression is that instead of omega 0 only, now we have omega 0 times alpha. So it's not the Fourier series coefficients that change, it's omega 0 that changes. Omega 0 changes to alpha times omega 0. Okay, that's it. So it's not the coefficients, it's the fundamental frequency. And that, of course, alters all the expression, and it makes a reproduction of the same or a similar signal in the more squeezed or a more expanded form. Only the fundamental frequency changes when you make a time scaling of a periodic signal. Consider this. You have a cosine. Remember that? Okay. Cosine omega 0 t. What were the Fourier series coefficients of this? It was 1 over 2 and 1 over 2. Because there were only two complex exponential terms for a cosine. 1 over 2 e to the j omega 0 t plus 1 over 2 e to the minus j omega 0 t. So the Fourier series coefficients are 1 over 2 and 1 over 2. If I change this frequency and make it alpha times omega 0, or if I change the time and expand the time by alpha times t, so it will make cosine alpha omega 0 t in general. What will be the Fourier series coefficients? Again, 1 over 2 and 1 over 2. That wouldn't change. The Fourier series coefficients will remain. But these omega 0s will be different. They will be alpha times omega 0 this time. So the Fourier series coefficients don't change when you scale the time. But as a matter of fact, it gives us a very strong argument that it's not enough to express a signal in terms of the Fourier series coefficients only. The Fourier series coefficients only by themselves will not describe your signal. You have to know the fundamental frequency omega 0 as well. And you can only combine the Fourier series coefficients with the appropriate complex exponentials at the proper frequencies, k times omega 0. So you need to know omega 0. Without knowing that, you can only reproduce the signal within a scaling factor. You will not know the frequency then. Okay. The fifth one is a little bit complicated. What happens if you multiply two time sequences? In other words, you have x of t having coefficients a, k. You have y of t and the coefficients are b, k. And by the way, these two must correspond to the same frequency or the period. So they are compatible. The k index refers to the same frequency in both signals, in other words. And let us multiply to obtain z of t times x of t times y of t is z of t. And what are the Fourier series coefficients of this z of t, which is, let's call ck? Can you understand that if this has a period 6 and this has a period 6, or frequency 1 over 6 and frequency 1 over 6, their multiplication will still be having the same period or the same frequency? Okay? So this k index will correspond to the same k frequency for both x and y and z. This one I'm not going to try to prove or illustrate the proof, although the proof of this one is also available. It's not very complicated, but it will take a lot of time. And it's not for the time being very important for us whether we know the proof or not. The proof will be of more importance in the general Fourier transform. We may consult to the proof over there. Over here, I'm going to give you the result, and the result will be, you have to be familiar with this result. You will see that it resembles something. This ck is summation over L from minus infinity to infinity, AL bk minus L. Do you remember this formula somewhere? Or would it make more sense if I write it like this? Now does it make sense a bit more? Convolution. Yeah. Strange phenomenon. These two, AL and BL, or AK and BK, these things, you may think of them as discrete time signals. They are vectors, infinite vectors perhaps. Maybe they don't end at some point, they go to infinity, but whatever, they are discrete time sequences. AK and BK are A of k and B of k. And in order to find the sequence ck, the Fourier series coefficient sequence of the multiplication in time domain, you have to convolve these two A and B sequences, and that's it. And this is a very commonly known phenomenon. When you multiply two things in time domain, you convolve the Fourier domain counterparts. Okay? And the opposite is also correct, by the way, we will see that. In other words, if you convolve two sequences in time domain, if you convolve them, then their Fourier transforms or Fourier series, whatever it may correspond to, are multiplied in the Fourier domain. So convolution and multiplication are two domain dualities. If you multiply in time domain, you convolve in Fourier domain. If you convolve in time domain, you multiply in Fourier domain. That's a very well-known, a very famous, celebrated observation that you will have to remember always. And this is the first time you encounter this duality, multiplication versus convolution in different domains. This is the first example. As I say, the proof is a bit long, so let's not go into the details of that. Now, the sixth property is with respect to the symmetry of the sequences. We said that if your sequence is symmetric, real and symmetric, like the example that we have solved already, then the Fourier series coefficients are also symmetric. A1 is equal to A minus 1, A2 is equal to A minus 2, etc. That is in general known as the conjugate symmetry. Although we work with real examples in most cases, the signals could also be complex valued. So this general form is more important for us. If x of t has Fourier series coefficients of ak, then x conjugate of t will have the Fourier series coefficients of a conjugate of minus k. And the proof is a piece of cake. Just write down the expression of x of t in terms of the summation k from minus infinity to infinity ak e to the jk omega 0 t. Then take the conjugates of both sides. When you take the conjugates of both sides, the right hand side will become k from minus infinity to infinity ak conjugate. This will be conjugated, and this will also be conjugated, but it has a certain conjugate, that is e to the minus jk omega 0 t. Alright? And since k is replaced by minus k in this expression, you make this substitution. L is equal to minus k, and L from minus infinity to infinity, a minus L conjugate e to the j L omega 0 t will be your new expression. And this new expression of x conjugate of t here, our new Fourier series coefficients are these. That's what it is. That's what it corresponds to. It's not only conjugating the Fourier series coefficient, but it's also inverting the index as well. So that is conjugate symmetry. But by itself, it doesn't mean much. We must elaborate a little bit further about how to use this conjugate symmetry property. Because we know that for real signals, the conjugate of t is equal to itself. X conjugate of t is xt itself. So it's like 6.a, for example. If xt is real, then xt is equal to x conjugate of t by definition, which means that ak is equal to a minus k conjugate, or you may take the conjugates of both sides and say that a minus k is equal to ak conjugate. So for real signals, this is a property that holds for every Fourier series coefficient. And notice that we usually do real signals. For example, what was the Fourier series coefficients, again, the place that I have just erased, of a cosine? Cosine omega 0 t. What were the Fourier series coefficients? a1 is 1 over 2, a minus 1 is also 1 over 2. Is a minus 1 a1's conjugate? Yes. a1 is 1 over 2, and its conjugate is also 1 over 2, because it's a real number anyway. How about a sine? What are the Fourier series coefficients of sine omega 0 t? 1 over 2j and minus 1 over 2j, right? Now, this is a1, this is a minus 1. Since sine is real, we must have a minus 1 to be equal to the conjugate of a1. Is it? Yes, it is. It's purely imaginary, so taking a conjugate means negating the imaginary part. So this is always valid for a real signal. And the final property, of course, these properties are just starting properties. We may expand or extend these things to other things. For example, if x of t is purely imaginary, then what would happen? Can you tell me? If x of t is not real, not complex, but purely imaginary, Then what can you say about AK in terms of A minus K? Then x of t will not be x conjugate of t. X of minus t will be equal to x conjugate of t, and you have to derive the property accordingly. But they are just candidate exam questions. So I'm not giving you all the properties here. I'm just giving you glimpses of important ones. And the last important one is so-called the Parseval's theorem. It tells us one important thing. It is possible to measure or evaluate the power of a periodic signal, not necessarily in time domain, but also in Fourier domain as well. So what was the power? This is the definition of power in time domain. The proof of this Parseval's theorem is, by the way, even more longer than the multiplication in time and convolution in Fourier. So the meaning, the essence of this is more important for us. It's not the proof that we care. The power in Fourier domain is nothing but, for all k, square sum of the Fourier series coefficients. So now you have to ask this question: which one is easier? And I will tell you this: you have to evaluate the power depending on whichever is easier. For instance, can you evaluate the power of a cosine waveform? What is the power of cosine omega t or sine omega t? You first need to take the magnitude square of a cosine, and the magnitude square of t, magnitude square of cosine omega t requires trigonometric identities. Okay, you have to look at the tables and things like that, and you have to evaluate over one period and normalize it by 1 over t. It is manageable. It is something that we already know. We know the answer to that already, fortunately. But isn't it easier in the Fourier domain? What are the Fourier series coefficients? 1 over 2 and 1 over 2. Two Fourier series coefficients. What is the square of 1 over 2? 1 over 4. What is the square of the other 1 over 2? 1 over 4 again. Sum them up. 1 over 2. So that's it. That is the power of a cosine. 1 over 2. It is a piece of cake if you know the Fourier series coefficients. And in fact, if they are finite, for sinusoids, they are finite. There are only two coefficients for every sinusoid. 1 over 2's and 1 over 2j's mostly. And these are magnitudes, as you see. We don't care about 1 over 2j's or anything. 1 over 2 is the magnitude over there. So the square will be 1 over 4, another 1 over 4. Just add them up. Evaluation of power is simple in the Fourier domain for sinusoids. For other signals, maybe it's easier in time domain. For example, for square waveforms, probably it is easier to evaluate the Fourier. It's easier to evaluate the power in time domain because the square of this, the magnitude is 1, is the same. It's the same thing. And the integral of this is just an area. So it's easy to evaluate the power in time domain if they are rectangular signals. So over there, I don't recommend that you evaluate the power of a rectangular waveform from the Fourier series coefficients. What were the Fourier series coefficients? 1 over 2, 1 over pi, 1 over 3 pi, 1 over 5 pi, 1 over 7 pi, all odd denominators, and you have to take the squares of them and sum them up. That's an infinite summation. It converges. It's a convergent infinite summation using Taylor series or something like that. You just evaluate that summation, but it's difficult. Then time domain will be easier. So what Parseval's theorem is saying us is that we don't care which is easier, just do the easier one. Evaluate the power of the signal in the appropriate domain. Now I said that during the time shifting property, we would use the property for an example. Let me at least give you that example, but that example will not be finished. We will stop in 5 minutes and then we will continue tomorrow. So the example is this one. By the way, these properties are all listed on page 206 in Oppenheim's book. I usually ask the students to take photocopies of tables from the book and bring them with you during the examination. Okay, the tables. So these properties are listed, tabulated somewhere. You can bring those tables to the exam. I'll tell you about that afterwards. The example is this. Okay. This is your signal. And what are the Fourier series coefficients of this signal? If this is 2, 4, -1, -2, etc. And the levels are 1/2 and -1/2. So what can we say about the Fourier series coefficients of such a waveform? This one I will call y of t, and I will start by the known version of it, which was x of t, I will say. 1. This was an example that we have previously solved, the only example again. And with respect to this x of t, first let's try to describe y of t, and using that relation between the two, this value is 1 by the way, between the relation between the two, using that, let's find the Fourier series coefficients of y. So what is y in terms of x? Y of t in terms of x is x of t minus 1 shifted to the right by 1, and then I subtract 1/2, because the values are, although not very proportional, sorry about that, this magnitude is 1, these magnitudes are 1/2 and 1/2. So if you shift this one to the right and subtract a half, you will get this shape. So this is the relation between the two, which tells me that for all k's except k is equal to 0, bk of y of t is equal to ak times the proper exponential term, e to the minus jk jk omega 0 t0. Okay, but what is t0? t0 is 1 because it is shifted to the right by 1, so t0 is 1. What is omega 0, by the way? What is the period here? The period is 4, so omega 0 is 2 pi over 4 or pi over 2. This is omega 0. So that would make ak times e to the minus jk pi over 2. That's it. The answer, the end. Except for 0. When k is not equal to 0, this is the answer. When k is equal to 0, things will change, and what you need to do is just substitute the ak that we already found in the example. Put it here, whatever that ak is, sine something divided by k times pi, wasn't it? And multiply it with this one. This is the answer. No further elaborations. But for k is equal to 0, the situation is a little bit different. As a matter of fact, if you shift your signal, level shift your signal by some DC value, only the zeroth Fourier series coefficient changes. The DC, A0 changes. And you have to evaluate B0 separately for this one. What is B0? There is no need to evaluate. Can't you see 0? Because the positives and negatives are balanced. If you integrate from 0 to 4, the positive and negatives will cancel each other, and you have to say that B0 is 0. So this minus 1 over 2 has that effect. It only pushes down the A0 from 1 over 2 to 0. This one has 1 over 2. A0 corresponding to x of t was 1 over 2. B0 corresponding to y of t was 1 over 2 minus 1 over 2, which is 0. Other than that, all the others are just plain shifted versions like this. We will continue with more elaborated versions of this example tomorrow. Okay? So let's stop at this point.